So with this presentation, we're going to have a look at some of the main issues involved with comparing mean values of different groups of observations and show you how to run it all in R and R Commander. But first of all, why would we bother comparing means? Well, in environmental assessment, it's often really important to see whether our mean value is different or not different, depending from some regulatory threshold value, for example the maximum permissible level or ecological investigation limit for some pollutant. That's a very important outcome of statistical testing, and it's pretty straightforward. We also need to assess whether, if we have a stratified sampling, for example, whether samples taken from different strata have different mean value than in other strata, or different sample types. So, for example, soil and road dust, or soil from around a wetland compared with soil in a park, for instance. Now, we use a one-sided test for the former application. So, and that's, as we'll see, usually t-test. And for two-sided tests, we have a couple of subsets, whether they're exactly two categories or more than two categories, and we use different statistical procedures. Both two-sided tests, because we need to use the whole distribution, but we used either a t-test or an ANOVA in that case. So first of all, the usual precautions. We already know about the first one, and that's skewness. We need to have data which are at least approximately normally distributed, and we should check for that visually and with the Shapiro and KS test statistics. And the other issue with means comparisons, particularly when we use analysis of variance, there is a version of the t-test which R Commander implements, which is not so sensitive to this, but we should really have equal variances for our variables. And the graph at bottom right shows some variables, particularly the curves with a mean at 0, where the mean is the same, but obviously the variance, or what we measure often is the standard deviation, and variance is simply standard deviation squared. Those variances are quite different. So we get a different statistical comparison, say with the green curve on the left, depending on our variance. So ideally they should be equal. Okay. We call equal variance homoscedasticity. Conversely, unequal variance is heteroscedasticity. Okay, so what do we need to do? Some preliminary testing. So again, I've mentioned the Shapiro and Kolmogorov-Smirnov tests. You always need to do those. We always, for means comparisons of the type that we're doing, need to have normally distributed variables. And something we haven't used before, which is fairly straightforward to do in R Commander, it's built in under statistics, variances, Bartlett's test. We can test for homogeneity of variances. Okay, and it'll bring us up a dialog box like that, showing our factors on the left hand side and the possible variables that we might want to check variance for on the left, and any factor will come up, not just those with only 2 levels, for example type, which in this data set's got soil and street dust as the levels. Group in this data set has, I think, 8 levels, and the Bartlett test can handle that as well. So the Bartlett test output looks something like this, and as with any or many statistical tests, we're testing against a null hypothesis, and our H0 in this instance is that the two groups have the same variance. So let's look at the example of barium in this data set, the element Ba. In this case, the probability of getting the results that we have, if the null hypothesis is true, that is, the groups have the same variance, is pretty low. So in that case, we can reject the null hypothesis as being quite improbable. Otherwise, we wouldn't get the difference in variance that we see. And so the variances are unequal, in this case at the 95% confidence level. On the other hand, and this is quite convenient, the same transformation which normalizes our data a log 10 transformation of barium concentration. Also homogenizes our variance, so now we have a homoscedastic, I can't even say that word, comparison. The p-value is 0.1, so we can't reject H0 at even the 90% level of confidence, let alone the 95%, and therefore we conclude that our variances are approximately equal, or equal enough to proceed with further statistical testing, which requires equal variances. All right. Okay, so the means comparison tests. First of all, the student's t-test. So the student's t-test is, I guess, a variation on the normal distribution. The t-distribution is another symmetrical bell-shaped distribution, but the t-distribution shown in the red curve on this plot here has slightly bigger tails. Okay, so there's more overlap at the edges, and it will actually be a little bit conservative in identifying differences compared with the true normal distribution, and that accounts for the fact that in most instances in the environment we don't have information about the population. We only have information from our sample. Okay. Analysis of variance works slightly differently. Calculates the variance within and between groups. So let's look at the graphical examples on the right, the lower right there. On the left-hand side, we've got an example where the variance within each group, shown by the dots of different colours here or clumped together, are small compared with the variance between groups. And the ratio of between groups to within groups variances are F ratio, or variance ratio, on which the probability is calculated. It's our F statistic for an analysis of variance. So in this case we'd have a high F, which would probably correspond to a significant effect of whatever the grouping is caused by. On the other hand, the graph at right shows a low F ratio. There's smaller between groups variance than within groups variance. So there's not likely to be a significant difference there, as you'd probably deduce visually from the data anyway. So let's have a look at the tests themselves. First of all, the single-sided t-test, where we can test for something like this. Is the mean zinc concentration in the ANVIL dataset, which we've had a look at already, greater than the ecological investigation concentration of 200 milligrams per kilogram? Just for your reference, this is taken from, I'm not sure if this is the most recent, but one of the more recent releases from DEC, which is now Department of Environmental Regulation, showing assessment levels for soil, sediment and water, and they actually resemble threshold values from much older documents, for example, ANZAC in 2000 or even before that. Anyhow, this is a clear example of a single-sided t-test comparison of our sample distribution with a single value, so only one side of the distribution is relevant, and we can click through this in our commander. Statistics means single sample t-test, and we will get a dialog box popping up. We can choose our variable. We just happen to know that we need log transform zinc to normalize it, and we put the log 10 value of the threshold in the null hypothesis box. So saying that our null hypothesis is that the mean is not significantly different from our threshold value, and we can be a little bit more specific in the test. We can certainly say that the mean is not equal to our null hypothesis mean, but we can also be as specific as testing for the population mean being greater than our null hypothesis mean, and that's what I've selected here. Okay, so the data are transformed. Log 10 200 comes from the threshold value, and we select the comparison that we want, and if we proceed with that, we get some output which looks something like this. Okay, so one sample t-test. In this case we've got a p-value of 0.09, so it's actually not a significantly higher concentration, even though the mean value is higher than 2.301. It's not a lot higher. And so we can't reject the null hypothesis at the 95% level, although we may be able to reject the null hypothesis at a 90% level of confidence if we're happy to be a little bit less precise. Alright. Just to note, we could also type this expression here, log 10 200, in the null hypothesis box, and would then calculate it for us. Okay, now two-sided t-tests, we need a factor with only two levels. We have one of those in the dataset. It's the factor type, and it contains the levels soil and street dust. So let's have a go at testing using a two-sided t-test, whether there's a difference in barium concentration between those two types of sample. So we click through statistics, means, independent samples, t-test. Here's our dialog box, the second box there, the middle one. So we select type and our transform variable. We select two-sided because we don't know the direction of the difference in advance. We don't know if one is less than the other or greater than the other. We usually choose a confidence level of 0.95, and notice that we can also select variances are equal or not equal. And the nifty thing about how R Commander implements the t-test is it actually uses a variation of it called Welch's t-test, which adjusts the probabilities in the case that each level of our factor results in groups with unequal variances. And that's kind of handy because we don't need then to be too fussy about our precautions. We should check just in case we want to use other statistical tests. And we get some output. Well, let's just go through that for a minute. The comparison is here, log barium by type, and here's our p-value, 0.01. So we can reject our null hypothesis that the two means are equal at the 95% level of confidence. And we also see that our 95% confidence interval for the difference between means does not contain 0, which also indicates that we have a significant difference at that 95% confidence level. And then the final piece of output is simply the two means. And if we want to have them in not log units, we could simply convert those back. So mean in group soil is 10 to the 1.007. Mean in the group street dust is 10 to the 1.247. Right. So we don't need to do the Bartlett's test of homogeneity of variances if we use Welch's t-test. Quite handy. Right. Sometimes, of course, we'll have factors with more than two levels, so 3 or more. But let's compare, first of all, the results. We can use ANOVA for factors with only two levels, and let's just compare the results from that with those that we got from our Welch's t-test. Fortunately, we know that the variances for log transform barium are homogeneous within soil and street dust, so we can validly do an analysis of variance on that. So to do that, again, statistics, means, as you'd expect, and one-way analysis of variance. We're not going to deal with multiple analysis of variance in this unit. Really, my view is that it's more relevant for designed experiments, which we don't encounter in environmental assessment, very much anyway, and we need data which are, I guess, more rigorously designed than we can often get from field observation. So one-way analysis of variance, and here's our output. So we get two blocks of output from running it in R Commander. First of all, a summary of the model, and you may be familiar with a standard analysis of variance table with the sources of variance at the beginning, the F value or the variance ratio, and then the probability associated with that variance ratio at the degrees of freedom that we have. And that's showing a very similar result to what we got from Welch's t-test. Not exactly the same p-value, but similar level of confidence, around about 0.01 probability, showing that the means are different at 95% confidence at least. And we get a table of means as well, with a little bit more information. The standard deviations are included, the number of data in each group, and the number of missing observations in each group. We wouldn't be doing ourselves justice if we didn't do some graphical checks. So we can use a box plot, especially if we modify the script to include notches. It gives us some useful information. But we remember that a box plot, the horizontal bar in the middle of the box plot, is not the mean. We can show the mean on this plot, but it's not as rigorous a comparison as the plot of means, which is also available in R Commander, and particularly useful if under the Options tab we select the 95% confidence interval. We don't get the same detail of information about the distributions as in the box plot shown on the left, but it more closely matches the statistics that we're doing. Okay, and if we want to fiddle about with our box plot and add a bit of script to it, so we make an object which has got our means in it, and give it a name, then make our box plot and add some points to that box plot, and usually tidy up by getting rid of the object that we created. This is just one way you can do it. There are other ways. We can indicate where the means are on the box plot itself. And look, if you wanted to go a little bit further with this and write a little bit more script, we could pop the 95% confidence intervals on there as well without too much more effort. Alright, analysis of variance when we've got more than 2 levels. So I mentioned already that our factor group has got 8 levels between it. There were 8 groups with valid enough samples in 2014. And let's have a look at manganese, and we'll log transform it to normalize it, and hopefully, although I didn't check this, homogenize the variances as well. We should check, but perhaps we'll do that after. Alright, so this is how we set it up. Again, it's a one-way analysis of variance, even though there's more than 2 groups. And it's useful to check this box here, pairwise comparisons of means, because if there is a significant difference overall from the analysis of variance, a standard analysis of variance won't necessarily tell us where that difference is. It could just be between 2 pairs of means, and the rest of them are not significantly different from each other. Or it could be the whole lot, we don't really know, but we can tell, and this runs the Tukey contrasts. It doesn't go so far as what some of you may be used to seeing, that's computing a least significant difference, but it does provide a lot of information. We'll show you that in a minute. Okay, so here's what we get for output from that, and you can see that again we get the standard analysis of variance table. In this case we get a highly significant effect of group on manganese concentration, a very low probability there to reject the null hypothesis with, and because there are lots of groups, 8 of them in fact, we get 8 different means. But it's likely that not all of them are significantly different. Look at group 8 and group 10. They're, to all intents and purposes identical, so they're probably not different, but the difference calculated by the analysis of variance is coming from somewhere else within that grouping. So how do we figure that out? Well, this is what the post hoc test, or the means comparisons, individual means comparisons does. And so you get a whole lot of output, which is interesting to go through sometimes, but the most useful part of it is this block of output here. The compact letter display, so-called, where we get a letter after each group. And let's just blow that up a bit and explain it. So if we get the same letter appearing under any pair of factor levels, they're not different at the 95% confidence level. So for example, group 3 and group 4 are significantly different because one has an A and one has a C, but neither of them are different significantly from group 5 because the A overlaps or the C overlaps. Okay, so we see how to do that. So it looks like most of the difference here is coming from groups 3 and 4. Right. Now we could say that group 3 is different from group 2 because there's no identical letters in there, and we can also say that group 4 is different from group 8. So group 4 having a C and group 8 having A and B, same as group 10. Alright, so that's a really handy way of quickly seeing which pairs are different from one another. We also get some other output as well, which can be useful to have a look at. And when you run the pairwise comparison, you get some more output in the form of a graph, which opens in your plot window, and we can inspect the confidence intervals for the difference between means for any pair of data. So here's group 3 and group 2. The confidence interval for that mean does not include 0, so they are significantly different at 95% confidence. But there are a whole lot of pairwise comparisons of means, particularly down the bottom end here, which do include 0, and therefore there's no significant difference between those means at 95%. Okay, we can also inspect our data with a box plot, which is not part of the standard output. We'd have to draw that ourselves, and notice I've put my little tweak on here and put the means on as well. And I haven't put notches on here because often the notches, when there's small sample numbers in each group, turn out to be bigger than the interquartile range boxes, and so the plots look a bit weird. Okay, one final thing which can be really useful. And we've talked about bimodal variables before, but also where some threshold might exist. Let's test whether there are different groupings, for example, depending on our distance from a main road. And we've got this minimum distance from a main road variable in there, well, we may as well use it. And what I'm going to do is make a factor about it, depending on whether our distance is between 0 and 100 meters, or any other distance, which will be greater than 100 meters. And we'll make two levels within a new factor. So I'm going to call the new factor road prox. So if we click OK on that, we will get a new factor, and it's a good idea to just check that you've got what you think you've got by running a summary. So summary anvil $ road prox, that's the name of our new factor, and it has two groups as we expected: close to main road and far from main road. Pretty intuitive, right? And then we can use our new factor in a mean comparison test. So let's change elements again, chromium this time. So what I've done is a Welch t-test, the default in our commander, on chromium, grouped by road proximity. All of the other things are just the defaults, and we get a p-value in this case of 0.16, so we can't reject our null hypothesis at the 95 or even 90% level. But you know, maybe if we'd chosen a different threshold for close and far, 200 meters or 50 meters or something like that, and that's something we can play around with. So the extra evidence that we don't have a significant difference is that the 95% confidence interval for the difference includes 0, so we don't have a difference in means, and we can kind of deduce that from our box plot, remembering of course that it's only approximate because the lines at the center of the notches are medians, but the notches have a degree of overlap that's probably too much, which gives us a visual indication on that the means are not significantly different. Final thing that we should have done initially is to do a homogeneity of variances or Bartlett test on our grouping of chromium with our new factor, and in fact our p-value doesn't allow us to reject the null hypothesis that the variances are equal, so that's all good, which is also supported by the box plot. The notches are roughly the same size. And that's about all we have to say about that.